Alright class, today we're going to finish up the surface area. This time we're going to talk about surface area for implicit surfaces. So this is the last sheet or two on the note sheet that I put up last week. So you can go back there to get the rest of this blank note sheet if you need to. There's some good diagrams here that basically tell you how they get the surface area. They approximate a little tangent square and then basically sum those up over the shadow region, as you can see there. And then they come up with how to get that stuff there. Again, the only thing you need to know is that if you have a function xyz equals c over a closed and bounded region R, then the surface area of that function is the double integral over the region, the shadow region, of the magnitude of the gradient of f divided by the absolute value of the gradient dotted with a p-vector. Now, what this p-vector is generally going to be 0, 0, 1, because the p-vector is a unit vector in the direction that is normal to the shadow region. So most of the time we make the shadow region the xy plane, and therefore everything that's perpendicular to the xy plane would be the z direction or the k direction if we're talking about the vector. So normally we're going to use 0, 0, 1 for the vector. By the way, this is considered, this stuff up here is also considered d sigma as well, this whole thing. It's another way to write d sigma. Okay, so now let's do some problems. Let's look at number 1. So these problems, this method of finding surface area is probably a little more cumbersome, but at the same time it's always the same steps. You get all these pieces of information and then integrate. So find the area of the surface of the bottom of the paraboloid that is cut by the plane z equal 4. Okay? Area of the surface cut from the bottom of the paraboloid and z equals 4. So first things we have is, what is the function of the surface? It is f of x, y, z is equal to, we're going to let this be x squared plus y squared minus z, because that's our paraboloid, the surface. So the first thing you want to find is the gradient. Remember, the gradient is just the partial derivatives. So the gradient of this surface is 2x, 2y, and then negative 1. We need to find a few other things. I look at my diagram here. The shadow region is the xy plane, so p, or the unit vector that we're going to need for our formula from up above, is going to be 0, 0, 1. Like I said, most of the time it's going to be that because it's the vector that is perpendicular to the shadow, and the shadow is this circle here. Oh my gosh, that was terrible. Alright, so that's P right there. Okay. Now, we also know, I should probably bracket this too as well. We now need to find two other things. We need to find the magnitude of the gradient, and we need to find what happens when you take the gradient and dot it with p. Well, we can actually do that one first. We need to find the absolute value of the gradient dotted with p. Well, when you're doing that, you're just multiplying the z coordinates, because x and y will cancel out. So you get negative 1, but then you take the absolute value of negative 1, and that's just 1. So that's nice and easy. So the only thing we have left is we need to find gradient of f, the magnitude of it, I should say. And that's just the square root of everything squared. Okay, so I get that. Okay, now I'm going to set up my surface area equation with everything I know. I know the surface area is going to be the double integral over that shadow region of, and if I look back at my formula, it's the gradient of f, the magnitude of it, which is the square root of 4x squared plus 4y squared plus 1, divided by, and then you look back to the formula, the value we got when we dotted p in gradient of f, which is 1, and then it's dx, the area, which is dx dy in this case, because that's what we're in. We're in rectangular. But since we have a circular region for shadow, we want to convert to polar, because remember, circles are easier to do in polar. So to convert this region into polar, First off, you should note that the bounds of this circle, this is x squared plus y squared equals 4. And I know that, by the way, because the plane z equals 4, if you put 4 in for z, you get the formula that the circle that will be projected down is x squared plus y squared equals 4. Which means that the radius goes from 0 to 2. Remember, it's always the square root of that number. And then since it's a circle around the origin, it'll go from 0 to 2 pi. Okay, so those are my new bounds. I now have to convert this equation into polar. If you guys notice, you can pull a 4 out. Well, not really pull it out, but we can factor it from the x squared y squared. And x squared plus y squared is r squared. So we get the square root of 4r squared plus 1. And then remember, dx dy converts into r dr d theta. So there is my new equation for the surface area. So I now have to integrate this. This is to the 1/2 power. So this is going to be a u substitution. I'm not going to go through the whole u substitution. When you do u substitution, though, this will become this whole thing still, and then it's going to go from the 1/2 to the 3/2. And so now I have to think about what I need here. I need a 2/3, but then I also need another 4, which is a 12. Oh, I don't need a 2/3. I just need a 1/12 there. Yes, 1/12. Okay. Because when you multiply, you would get 3 over 24. And then when you take the derivative of the inside, you then get a 8r. So when you multiply that by 8, you get 24 over 24, which is 1. So that'll cancel out. I was only doing the 4 in my head, and I was forgetting that you also have this extra 2 when you take the derivative of that. And then the r will be there, so that r will come from there. Alright, so that would be the integral of this. And I'm evaluating that from r of 0 to 2. So now we're just doing some double integrals from before. So I put a 2 in, I get 4, 16, 17 to the 3/2. So I get a 1/12 times 17 to the 3/2 minus I put a 0 in, and I get a 1 d theta. And again, this is from 0 to 2 pi. Alright, so now I integrate. This is all a constant. So basically it's all this times 2 pi. So it's 2 pi times, this thing I had just now. So my final answer for this problem is the surface area of the bottom part of the paraboloid, once you cut it off at z equals 4, is pi over 6 times 17 to the 3/2 minus 1. Not pretty, but it is an exact answer. Again, the only thing that's important here is knowing how to do the setup and solving. So again, getting all the pieces we needed, the gradient dotted with the unit vector that's perpendicular to the shadow region, and then the gradient, the magnitude of the gradient as well. Everything from here on is just stuff we've done before. Okay? Alright, let's do one more, because I only have 15 minutes max, so let's do that. So find the area of the cap cut from the hemisphere and by the cylinder. Okay, so this is kind of like the problem we just did. We have to figure out what the surface is that we're trying to find. Well, we're trying to find the top of this cap. So that is the hemisphere. So that's from this equation right here. So my f value, my f equation, is just going to be x squared plus y squared plus z squared, because that's the surface, which means that the gradient of f is 2x, 2y, and 2z. So now I have that. Again, the shadow will be just this circle. Since it's cut from the cylinder, x squared plus y squared equals 1, the shadow will be just a circle. And therefore, the p-value is again going to be 0, 0, 1, because it's perpendicular to the xy plane. So p is that. Let's find the absolute value of the gradient of f dotted with p. Well, it's just 1 times 2z, so we get 2z. So we have this piece. We also need the gradient, sorry, the magnitude of the gradient. So we get 4x squared plus 4y squared plus 4z squared. Now, we can actually make this better because since the hemisphere has a set value, we can actually use that to simplify this integral, or this equation here. First off, we can factor a 4 out of everything, and when you take the square root of 4, it becomes a 2. And I'm left with x squared plus y squared plus z squared. But we know that for this problem, x squared plus y squared plus z squared equals 2. So therefore, the magnitude of the gradient of f is 2 root 2, which makes things a lot easier when we do this problem. So, next we can set up our surface area equation. So the surface area is the integral of the region, which is the shadow region. We'll deal with that in a second. It's the magnitude, which is 2 root 2, over the gradient dotted with p, which is 2z, and then it's dA. So the 2's cancel. And here's the problem. We have z. When you're integrating, the shadow region is not in terms of z, it's in terms of x and y. So we need z. We can't have this z. We need z in terms of x and y. So therefore, we go up here and we solve this, and we get that z is equal to the square root of 2 minus x squared minus y squared. And that just comes straight from this equation up there. So therefore, the surface area formula becomes root 2, I'm pulling that out just because it's easier, 1 or dA over the square root of 2 minus x squared minus y squared. So now we're here. Again, since this is a circular shadow region, we need to make it polar because it's a circle, make life easier. So I have this is equal to root 2. For the shadow region, it's 0 to 1, 0 to 2 pi. The top becomes r dr d theta. The bottom becomes the square root of 2 minus r squared. Okay, so this is another u substitution one. I'm running out of time on the video. You make u this, and then go from there. What ends up happening is that you get that when you do the integral, you get the square root of 2, sorry, I don't know why I did that, 0 to 2 pi, and then this becomes negative 2 minus r squared to the positive 1/2. When you integrate it, it popped back up. And we're evaluating that from 0 to 1. And then there's still a d theta. So I kind of skipped some steps there, but that's... Whoa, where'd you go? So I skipped some steps, but that's where it went. When you plug that in, you end up with a square root of 2 integrated from 0 to 2 pi. When you simplify everything and distribute the negative, you get root 2 minus 1 d theta. So what ends up happening is when you integrate, the surface area becomes 2 pi root 2 times root 2 minus 1, which you can actually simplify into 2 pi times 2 minus root 2. Okay, so again, the hardest part about this is not the setup, even though you have to do all that work, it's actually the integrating, which is stuff we did before. You'll have to do u sub, you'll have to do that. Alright, well that is how you do implicit surface area. You do not have to parameterize the surface, you just go with what you're given. So the next 3 days you will have a problem a night. Tonight starting with problem 1 on the worksheet. And then again you'll have to submit problem 2 the next day and problem 3 the next day. Those will be your checks. Okay? If you have questions, please email me and I will set up a conference and we'll talk through it. Talk to you later.